Bismillahirrahmanirrahim. Dear students, today we are going to discuss some short question regarding CC bond generation. These lectures are organized to revise some points during these lectures, some points of these lectures, and also the minimum requirement for the number of lectures was 40, so we decided to present some short questions on these three classes of reactions, including CC bond generation, C double bond C, CN, and in the end CO bond generation. So this is the first lecture about the CC bond generation short questions. Question 1 is what are the different CC bond generation reactions without organometallic catalyst? That is, these are the CC bond generation reaction which were included in our syllabus, and these reactions did not include or use organometallic compound as catalyst. Two reactions comes under this heading. Number 1, Baylis-Hillman reaction, and second is the Willsmere-Hack reaction. In the Baylis-Hillman reaction, we used an electrophile and an activated alkene, and after the reaction of these two in the presence of tertiary amine as a catalyst, we get the CC bond generation between these two compounds. And in case of Willsmere-Hack reaction, aromatic system having electron donating groups are used for the formylation with the help of dimethyl formamide and POCl3 or phosphorus oxychloride or phosphoryl chloride. Having some temperature and also time is required for this reaction, and we get the formylation of the aromatic system that may be at ortho position and can be at para position. Depending upon the feasibility, there can be one substitution or one type of product also. Question 2, what are the different CC bond generation reactions with the organometallic catalyst? 4 different reactions we have discussed in our syllabus, which include the CC bond generation in the presence of organometallic compounds or organometallic catalyst. First was the Kumada cross coupling reaction, which used alkyl halide and Gigner reagent in the presence of palladium using ether as solvent, and we get the CC bond generation along with magnesium halide byproduct. Second was the Negishi cross coupling reaction, which also used alkyl halide, but in place of Gigner reagent it used organo-zinc compounds, and which yielded the CC bond generation along with zinc halide as byproduct. And third was the Suzuki cross coupling reaction, which was also using alkyl halide, but with organoboranes, which are known to be the cheapest reagent among these three, that is Gigner reagent, organo-zinc reagent, and then organoboranes. So by using the organometallic catalyst and also base, we obtained the CC bond generation. Fourth one was the Heck reaction. Heck reaction is also basically about the CC bond generation, but in this case the CC bond generation is between two carbons, in which one carbon is of an aromatic system and second carbon is a sp2 hybridized carbon, that is double bonded carbon. So single bond, CC single bond is generated between two carbons which are already making double bond with other carbons. Here are some typical questions between with these reactions, and among these reactions, first one is from Baylis-Hillman reaction. The question is, what is the role of electron withdrawing group in Baylis-Hillman reaction? As we know, electron withdrawing group is present on the alkene to form it an activated alkene. or the question can be why there is attack of DEBCO. DEBCO was the tertiary amine which was used as catalyst on beta carbon instead of electrophilic carbon of electron withdrawing group. Here you can see the reaction in which nitrogen of DEBCO with its lone pair is attacking on the beta carbon of alkene instead of the carbonyl carbon of the ketonic group. So the question is why the attack is on this beta carbon, not on carbonyl carbon. First point, electron withdrawing group is attached to carbon double bond and thus increases the electrophilic character of beta carbon through conjugation. And second point, here you can see the conjugation shown at the end of the slide, where after conjugation the beta carbon is getting the full positive charge, and that is more electrophilic character. Second, the conjugation also shields the nucleophilic attack of base like DEBCO on electrophilic center of electron withdrawing group. That is why their attack was not on the electrophilic carbon, because this resonance, this conjugation shielded that carbon of carbonyl group, and so the nucleophilic nitrogen is attacking on the beta carbon, which is open and more electrophilic as compared to that of the carbon of carbonyl compound. Here is another important question, that why DEBCO is acting upon activated alkene and not the electrophile in balanced element reaction. We have two regions, one is aldehyde and second is the alpha beta unsaturated compound, that is we are calling it as activated alkene. He is saying that when both of the regions are present there, then why DEBCO, that is our catalyst tertiary amine, is going to attack on the alpha beta unsaturated compound instead of the electrophilic, like in this case here you can see the benzaldehyde. When there are two such regions are present in the reaction, and the attacking region or catalyst can interact with both of the regions, then there is the principle or rule, there is the way of the reaction is in this way, that we first add one region, and after getting its intermediate, then we add the second region. Here is this case DEBCO and the activated alkene are stirred first with each other to form the enolate ion, and then the second electrophile is added to that enolate ion for further progress of the reaction. Question 5 is about Willsmer-Hack reaction, that why electron withdrawing group are not recommended on aromatic system in Willsmer-Hack reaction. Here you can see a side reaction by this electron withdrawing group present in the aromatic system. Here is carboxylic acid. If carboxylic acid is present on the aromatic system, then it can interact with the created iminium cation intermediate, and we get the final product of amide, or you can say the formamide, along with the acyl halide, and thus we are not going to the product side, which is the main reason or main function of the Willsmer-Hack reaction. So therefore electron withdrawing group are not required for the Willsmer-Hack reaction, and another important thing is that they decreases the rate of the reaction also. Next question is, can we use some other chlorinating agent instead of POCl3 or phosphoryl chloride or phosphorus trichloride in Willsmer-Hack reaction? Yes, a number of chlorinating agent can be used to produce the intermediate iminium cation. For example, here you can see the acid halide generated from carboxylic acid, oxalyl chloride generated from oxalic acid, phosphoryl chloride or phosphorus oxychloride created from phosphoric acid, which is already used by the Willsmer-Hack reaction, and also thionyl chloride or sulfurous oxychloride generated from sulfurous acid. If we use the oxalyl chloride, then this oxalyl chloride, here you can see the reaction of oxalyl chloride with the dimethyl formamide, and the progress mechanism of the reaction is same as we have discussed during the lecture, but here this reaction is given to show to justify that after the reaction of this oxalyl chloride and a number of steps we obtained the aminium cation intermediate with the formation of certain byproducts. Another question from the step 1 of Willsmere-Hack reaction is given here. Mechanism is shown here also with the nomenclature of step 1, 2, 3 and 4. Here you can see the step 1. In step 1 there is attack of oxygen on the phosphoryl chloride instead of the nitrogen, although we know that nitrogen is more nucleophilic as compared to that of oxygen. The question is why attack on phosphorus is through oxygen instead of nitrogen. So we answered it in this way, that nitrogen is more nucleophilic, no doubt, and due to this more high nucleophilicity, the lone pair of nitrogen is resonating towards the carbonyl of this dimethyl formamide, and the oxygen is getting the negative charge. This negative charge oxygen then attacks on the phosphorus of the phosphoryl group, and nitrogen is more nucleophilic, but due to this conjugation, oxygen is getting negatively charged with sp3 hybridization, and so attack on the phosphoryl phosphorus is through oxygen instead of nitrogen. Another question from the given step 2 of Willsmere-Hack reaction mechanism, that why PCl bond is broken and not PO bond. That is when after the attack of DMF on the phosphoryl chloride, we get the intermediate in which oxygen attached to phosphorus is negatively charged, and when this negative charge comes back to phosphorus, it is making double bond, and at the same time PCl bond is breaking and we are getting Cl minus ion. The question is the question is here that when oxygen negatively charged oxygen is going back to the phosphorus and making their double bond, then there are two chances: either PCl bond is broken or either PO bond is broken. But if PO bond is broken, then number one, we are going back to the reactant side, and if PCl bond is broken, then we are going to the product side. Number one thing. Number two, if you compare the bond energy of these two bonds, then PCl bond is 326 and PO bond is 335. Although this is a very small difference, but our point is justified by this bond energy, that PCl bond has less bond energy, so it will be broken is first as compared to PO bond. Another question from this step 3, given step 3, is that why chloride ion is attacking on the double bonded carbon instead of double bonded phosphorus. Here you can see the phosphorus is attached with 2 oxygen, 2 chloride, and it is also double bonded, and at the same time chloride ion is attacking on the carbon, which is also double bonded, but it is attached with 1 nitrogen and 1 oxygen. One thing is the difference, is the basic difference is as hybridization, because the carbon is sp2 hybridized and the phosphorus is dsp2 hybrid due to involvement of d orbital for the hybridization. Although phosphorus is attached to 4 electronegatives, 2 chloride and 2 oxygen, 4 electronegatives atom, and its electronegativity is also low, that is 2.19 more electropositivity than that of carbon. But this in hybridization, due to involvement of d orbital, there may be decrease in the electrophilic character of phosphorus, and the carbon having sp2 hybridized hybridization, although its electronegativity is little bit higher as compared to that of phosphorus, but it is attached with sp2 hybridized nitrogen and then sp3 hybridized oxygen. So carbon is showing here more electrophilic character, or you can see by the resonance, if the double bond of is shifted to nitrogen, this carbon is getting the full positive charge, and so chloride ion will be attracted towards this full positive charge. Another reaction question from Willsmere-Hack reaction mechanism is that why CO bond is broken and not CCl bond in step 4. Last step here shown here with the name of step 4. and the question is why only C O bond is broken and not CCl bond. If CO bond is broken, which is shown here, and you can see the formation of iminium cation and also the phosphorus oxychloride with the negative charge on oxygen, which is also resonating towards the other oxygen, so this anion is stabilized through conjugation. But if instead of CO bond, CCl bond is broken, which has also little bond energy as compared to that of CO, but in that case we shall get chloride ion, which is less stabilizing as compared to that of this phosphorus anion. So we can say that the bond energy is not only mattering the reaction, but also the stabilization of the product is also mattering here. Here you can see the another mechanism, reaction mechanism from Willsmere-Hack reaction. Here step 3 and step 4 are nominated here. In the step 3, the question is here that why proton is removed by water instead of chloride ion. You can see here chloride ion is also present along with this positively charged oxygen, but the proton from this oxygen is abstracted by the water. Although chloride ion is also nucleophilic, water is also nucleophilic, but as we know that water is in excess as a solvent, so excess region, there are more chances for the excess region to act as a nucleophile and abstracts the proton here. Another simple question from this Willsmere-Hack reaction mechanism here in nominated step 4 is that here you can see the attack is from the lone pair of nitrogen instead of the lone pair of oxygen of hydroxy group. So simply we compare the nucleophilicity of both nitrogen and oxygen, and we already know that nitrogen is more nucleophilic due to its large size as compared to that of oxygen and less nuclear charge. Next question is about Kumada cross coupling reaction, that why THF or ether tetrahydrofuran or ether is recommended as solvent for Kumada cross coupling. We know that in case of Kumada cross coupling reaction we are using Grignard reagent along with the alkyl halide, and Grignard reagent are active species due to polar bond of carbon and magnesium atom. So this Grignard reagent is kept in dry ether to avoid its reaction with moist. And another thing which ether gives here is the stabilization point. Here you can see the stabilization of this Grignard reagent through ether. The stabilization of Grignard reagent through ether can be shown here through figure, that magnesium atom is accepting two lone pairs from two molecules of ether functionality or ether compound, and so it is stabilized by this conjugation also, this coordination also. How magnesium can form these two more bonds? Here you can see its electronic configuration, that magnesium has two electron in its s orbital. When this one of the electron is shifted to px, then it is getting two unpaired electron in excited state, so making two bonds, one with the R group and one with the X group. And then the two p orbital py and pz are empty here, which can get the lone pair of oxygen or oxygen from ether molecules can coordinate in these empty orbitals of the magnesium. Here is the simple revision of the basic question, that what is the oxidative addition step in all the class coupling reaction. We know that oxidative because palladium is oxidized to from 0 to +2 oxidation state, and additive because RX compound is added to this lead in a concerted way. At the same time old bond is breaking and new bonds are forming, and we get the square planar geometry of palladium with R and X at transpositions to each other. Another important questions regarding the next step of transmetalation in these cross coupling reactions. Here the example of Komada and Negishi cross coupling reaction given here. In this the question is why there is no shifting of other halogen to palladium instead of R in transmetalation step. Here you can see in the first step R1 is shifting from Grignard region to palladium and X from organometallic compound to magnesium. Similarly in the second reaction R1 is going to palladium and X from organometallic compound is going to from palladium complex to zinc. The question is why X from the zinc is not going towards the palladium. Similarly X from the magnesium Grignard region is not going towards the palladium. This thing can be explained because Z and X bond are strong bonds because zinc and magnesium are good metals than palladium, and also therefore due to good metallic character they have a high affinity for the halogen halide as compared to simple covalent bonding. So therefore X is moving towards the magnesium or zinc, and R1 group is moving from the magnesium or zinc towards the palladium. Next question about these cross coupling reactions: what do you mean by reductive elimination? Reductive means palladium is being reduced from 2 oxidation state to 0, and at the same time the R and R1 groups attached to palladium are removed through elimination. So therefore it is termed as reductive elimination, and this elimination is also follows a concerted mechanism in which all bond making breaking goes simultaneously, and we are obtained with the R1 group and also the palladium complex with 0 oxidation state. In case of Suzuki cross coupling reaction, we know this reaction in which boron normally form 3 bonds, it is okay, but here you can see in this reaction boron is forming 4 bonds with a negative charge on boron. So question, how 4 bonds of boron can be justified? Here you can see the electronic configuration. Boron with electronic configuration is shown in ground state. It has 1 unpaired electron, but when 1 electron is shifted from 2s2 to 2p0, then we get 3 unpaired electron making 3 bond, but 2p z orbital is empty, and this orbital can attach or can acquire a lone pair through coordinate covalent bond. Here you can see the case in which OR2 minus from sodium base is coming towards the boron and making their coordinate covalent bond. So therefore boron is getting the negative charge due to the negative charge of this alkoxy group. Another important question, the last question of today's lecture is about the Heck reaction, that what is the nature of the bonding in coordination step of Heck reaction. You know that in Heck reaction we used an alkene which was coordinated, which was making the single bond with the other region of alkyl halide or aryl halide. Here you can see the bonding dashed line showing the interaction between the double bond of alkene and the palladium. This interaction can be of 2 types. Number 1, pi donation from HOMO of alkene to empty orbital of palladium, because HOMO of alkene has 2 electron filled, which is making coordination towards the empty orbital of the palladium. This is known as pi donation. And second is the sigma donation, which is from the metal towards the LUMO of alkene. Here you can see the MOT diagram also. The first type, pi donation, is shown with also termed as pi acceptance, and second sigma donation is also shown here, in which metal is donating the pi lone pair of electron towards the LUMO of alkene. So this is the all about of today's lecture, some short question regarding CC bond generation.